On behalf of the Indian Academy of Sciences, I have great pleasure in welcoming you all to the 28th mid-year meeting of the Academy.
On different kind of photophysical interaction of the nanomaterials, so when the light interact with the different kind of nanostructure materials, but eventually we try to develop different kind of light harvesting system based on the nanomaterials. So because this is now a very challenging problem to mimic some photosynthetic process so that we can convert the solar energy to renewable energy. So different emphasis has been given on nanomaterial-based light harvesting system. So different strategy has already taken based on the quantum dot, because quantum dot is a well-established system in nanomaterial where you can excite and you can generate the exciton, and that exciton can use for the light harvesting system. Even metal nanoparticle can use for different kind of different devices. Semiconducting metal heterostructure system people are using for different kind of charge separation purposes to generate photovoltaic or photoelectronic application. Even recently people are working on semiconducting polymer nanoparticle. This is pi conjugated system. So there is a homo-LUMO gap. You can manipulate the excitonic dynamics. You can manipulate the excitonic diffusion process. That is very useful for the optoelectronics application. This organic inorganic composite also very important material nowadays for developing different kind of light harvesting system. People now working on also porphyrin nanoparticle or nanostructure based, because porphyrin molecule can absorb the visible light. So by using the solar light you can dissociate the charge and you can use this for solar cell application. And basically we are working on all these different kind of nanomaterials, nanostructure materials. Because why people are interested on nanomaterials? Because all the photosynthesis process, you have to have antenna material that will absorb the light and that will dissociate electron and hole, that will you can transfer or you can recombine. This is the process. But in case of antenna material, very good antenna material, this nanomaterial is very useful because they have a high molar extension coefficient. That means that light will absorb more photon will absorb, and they are very photostable. That is well known, and easy to transfer its energy. So you can have energy transfer process or like this. So most fundamental process in the light harvesting system, if you go to the literature, you will find out three important photophysical process. One is the exciton dynamics. You have to know the charge transfer and the energy transfer process. These three important photophysical process for any kind of light harvesting process. So what is this? So this is first recombination process. If you have a semiconducting quantum dot or semiconducting material, when you put the light, that will the electron goes from here to valency to conduction band, and if they will radiatively combine, then that will generate light. But in most of the cases, the non-radiative process more prominent than the radiative process. In that case, what happens when you excite, that electron goes to higher orbital and that will non-radiative and that will not recombine. That's why in semiconducting system or any optical material, when you put one photon, you will not go to one photon. That's why you will get the quantum will always 0.2, 0.3, 0.5 like this because of the non-radiative process. So that's why the exciton dynamics is very important to understand for developing any efficient light harvesting system. Second is the charge transfer, charge separation, because people are now interested on hybrid system in any kind of graphene hybrid, quantum dot graphene, polymer graphene. But in most of the cases, what happens when you oxide the system, that will generate electron on hole, and that will transfer electron and hole A to B or B to A. So that charge transfer is very helpful for the photovoltaic and photocatalysis or for the solar cell application. Next one is the charge transfer, energy transfer. So if you excite, then that will transfer to the donor to acceptor. These are the most important fundamental processes for all light harvesting system. And we try to understand all three important phenomena in nanomaterial system. So in case of photovoltaic application, very, very simply, you have to excite the semiconductor, semiconducting nanoparticle or any material. Then if you take it out, that electron in the anode and cathode, the hole in the cathode, you will generate the photocurrent. That is the basic principle. You will not allow them to recombine. That is the charge separation kind of thing. But in case of photocatalysis, same thing, that electron if you use for the reduction purpose and hole for the oxidation purpose, then you can generate hydrogen, right? So any kind of photocatalysis you can do. So these are the most important fundamental processes, and we try to understand all these dynamics by using the ultrafast and ultrafast spectroscopy. Now today I will discuss little bit on exciton dynamics, then I will discuss about the interfacial charge transfer, then I will talk about the energy transfer, and few systems I will discuss. First I will talk about, recently we wrote a review article for a special issue on light harvesting, where we discuss in different systems on semiconducting quantum dot, metal nanoparticle, semiconducting metal heterostructure, what is the challenging issues and what is the current status for making any efficient light harvesting system. Now I will discuss the exciton dynamics. The main important issues in case of exciton dynamics process, in case of nanomaterial-based system, the question is that shape, size and composition we know, if you change you can tune the optical property, you can tune the photophysical property. But whether that will influence the carrier relaxation process or not. And how the surface trap state influence the decay kinetics due to the curvature or lattice strength because of the composition. I'll give two examples later on. Finally, we develop a very modest model to explain all these things. So far there is no model to explain the non-radiative process and radiative process, the kinetics of this exciton. These are the two examples when one cadmium solid spherical rod shape and triangle shape we prepared. That is very important. They are very easy by changing the composition. Another example is the same size but different composition of this alloy structure. Now we want to correlate the carrier relaxation dynamics, whether that will influence by the shape or the composition, because in case of alloy structure, because cadmium and zinc different parameters, crystal lattice parameters. So when we increase the composition, the lattice parameter induce the lattice strain, and that will make some trap state. We try to correlate the trap state, whether that will influence your decokinetics or not. In case of different shape, spherical shape, because in case of spherical, if you want to make a quantum hill, you will always get higher quantum hill in case of spherical rather than the asymmetric shape. Because why? Because in case of spherical, there is no surface curvature. But in case of rod shape or triangle shape, there is lot of surface curvature. And we believe all this surface curvature creates lot of trap state, and that will allow for non-radiative radiation, and that's why the quantum is very low. And I will explain this one. This is the quantum dot again, I want to explain again. This is the valency and conduction band, and this is the trap state. This is the trap state. If your quantum dot is very good, then only you can consider the trap state, not surface defect state. I am considering only the trap state because our quantum yield is very good, and the full width half maximum is 25, that means very good quantum dot. So when we accept that electron goes from the valency to conduction, they will recombine, they will generate a light. This is a radiative process. Now, if that electron goes to the trap state and they will recombine, they will not generate a light. This is a non-radiative process. Now, the question is that if we can understand the rate kinetics for the radiative recombination or the non-radiative recombination, then you can find out how many trap state is there in your system. And based on this, you can correlate the number of stat influence your non-radiative process. So this is the simplest model, and we try to understand all these rate radiative rate constant, quenching rate constant, non-radiative rate constant, and obviously ligand you have to consider because different kind of ligand you have to use for preparation to stabilize the nanoparticle. So there is a probability of charge transfer takes place. Considering all these points, and there is a one assumption, the number of trap state on the nanoparticle follows the Poisson distribution, and then we derive an equation, and we try to fit it this curve. This is for spherical, this is for rod, and this is for triangle, and we try to calculate the number of trap state over here. In case of spherical, it is 11.2. In case of rod, 21 or 22. In case of triangle, 34. That means the number of trap state increases from spherical to non-spherical, and that will actually enhance the non-radiative process. That's why your quantum is very low in case of non-sphericals from spherical to non-spherical process. But in case of lattice, if you change the lattice state by alloy compound, this is the very good material for nonlinear optics or for charge separation. But we have correlate the number of trap state increases with the lattice stain, and that lattice stain actually correlate with the radiative or non-radiative stuff. So these are the important contributions from our group. Now I will talk about the interfacial charge transfer in case of hybrid system. That is very important for nowadays for making any kind of devices, for optoelectronics, for solar cell, for photovoltaic, for photocatalysis. And we have developed few systems. This is graphene with the polymer nanoparticle system. Here we have observed the electron transfer process. These are the two important processes in case of charge transfer, either electron transfer process or hole transfer process. In some cases, both process takes. So here the quantum polymer nanoparticle with the quantum dot, we try to understand the whole transfer process. I will come to the point, next slide. This polymer nanoparticle with gold nanoparticle, there is electron transfer process that will enhance the photocatalysis process. This is porphyrin rod with the graphene, we generate very good photocurrent, that is manifold increase of the photocurrent because of the charge separation when electron transfer from the porphyrin to the graphene oxide state. Now I will give one example. This is example for the electron transfer process. Recently we prepared this nano rod. This is alloy nano rod, because this alloy nano rod we prepared because NIR range emission band of this. We try to attach this quantum dot on the porphyrin sheet, but it is very difficult because graphene oxide is negative and porphyrin, this is also attached with some ligand, but you cannot attach. That's why here we use the porphyrin molecule to wrap the nanoparticle in pi-pi interaction with the graphene oxide. The important thing is that whether it is electron transfer process or hole transfer process, how do you know? First you have to know the band diagram. That is very important to know, because in case of porphyrin, when you excite, this is the homolumo gap and this is the quantum dot, this is the we measured from the CV, and this is the work function of the RGO. So when you excite the porphyrin, that will transfer the electron here, and in presence of quantum dot there is a cascade kind of electron transfer process, and we have measured by ultrafast spectroscopy what is the rate of the electron transfer process. Based on this, we have seen there is a photocurrent generation, and because of the charge separation, because electron transfer from the porphyrin to the graphene state. And from the ultrafast spectroscopic study, we have seen there is 25 picosecond takes from porphyrin in this system, but when you put the quantum dot, that the very fast electron transfer process, because cascade electron transfer process, this 5.58 picosecond. As a result, you can generate a photocurrent, 200-fold increase of the photocurrent. That material could be used for the light harvesting system. But as a proof of concept, we have measured the photocurrent, that there is a charge separation takes place when you excite by the visible light. That is because of the porphyrin molecule. Now I will come to next one. This is again on the hole transfer, right? So we have prepared the NAHPPV nanoparticle because we are interested on nanoparticle to control the excitonic diffusion process. I will not discuss on that. But this polymer nanoparticle, when you make it, always you get the negative charge. So you cannot attach the quantum dot with them. But using the chemistry, we can make it positive by using this hexadecylamine, and negative charge of the quantum dot we attach electrostatically. And two different kind of quantum dot we have prepared, two different size. We try to understand whether it prefers the electron transfer process or hole transfer process. But before that, we have calculated the homolomo gap of the quantum dot valence chain conduction band, and very interestingly, for different size 2.1 and 3.8 size, this is the band gap. In case of polymer nanoparticle, this is the homolomo gap. So when we excite, always there is a tendency of Hall transfer process. Now the question is, for different size, what is the Hall transfer rate for different nanoparticle? Do you know? We don't know so far. From the decay time, from the ultrafast spectroscopy by the ultrafast upconversion and the pump probe experiment, and this is the PL. There is a 98%. This is the 3.8% PL quenching for different size, and we have seen that Hall transfer is 390 femtosecond in case of Hall, 120 picosecond. So rate depends, Hall transfer process depends on that. This another problem is that Hall and electron both can use in your system. This is a very interesting system, recent work. This is the carbon dot, this is ZNO. I will come to this one. This is the valence chain conduction. When we excite the ZNO, there is a Hall transfer process. But in case of carbon, if you excite the carbon, there is a electron transfer process. And you have very good 11-fold photocurrent increase because of the charge separation. So based on using the Hall electron and electron Hall transfer, you can make it different kind of devices, which is very useful for any kind of device, photocell, photovoltaic cell or solar cell application. Now I will come to the last one, that is the energy transfer process. Why quantum dot people are interested on energy transfer process? Because biology people are using 1:1 interaction, one donor, one acceptor, 1:1 interaction. But in case of nanoparticle, what happened? Because of the size of the nanoparticle, it can interact with different kind of dye molecule. So you have n number of dye molecule can interact. It depends on the surface of the nanoparticle. So we have addressed a lot of issues in our previous work. But here I will explain one light harvesting, pure light harvesting system. This is like a protein pigment interaction. We prepared a polymer nanoparticle with dye and BSA protein with Nile red dye, and we make a complex kind of thing. So because why we choose this is coumarin emission absorption, emission of the PVK host is exactly matches with the absorption band of the 153 dye, and that emission band of the 153 exactly matches with the absorption band of the Nile red dye, so that there is a overlap. There is a chance of energy transfer process. This is the polymer nanoparticle, this is the Nile red dye inside the 2A domain in the BSA protein. Now the question is that whole decay kinetics we have done. When you excite only the PVK nanoparticle, you will get the blue emission. That is the blue emitting stuff. But when you put the dye molecule inside the polymer matrix, if you excite the polymer, that will energy transfer from the polymer to the dye, and you will get the green emission that takes 350 picosecond. That energy transfer takes place. Now the polymer nanoparticle with the Nile red dye with the BSA, there is a complex system. If you excite the polymer nanoparticle, that energy transfer takes place. There is a red emission due to the Nile red dye, that is 241 picosecond. But overall, if you excite the Nile red, then you will get the white light emission. So that is a very important system for light harvesting, very complex and very cascade kind of energy transfer process. But in this case, we have measured the antenna effect, that is very useful for the light harvesting application. You don't go on all this stuff, but in this case, we have antenna effect 31, that is very good value with the very low concentration, and the effective extension coefficient is 80, that is in the literature unprecedented. So there is very simple system we have developed where real light, artificial light harvesting system we can generate. The last one is the again carbon dot with BSA protein cap gold nanoparticle. We try to develop another new system and try to understand all the photophysical interaction. So here we develop also white light, and this is the carbon dot because of the blue emission. I will not go into the detail all this stuff. This is the gold cluster made by the BSA protein capped. So, and when you attach with the BSA protein and carbon dot, you will get only the 63% energy transfer takes place from blue to this red one. So there is overlap. But we try to improve the efficiency because 63% is not good. That's why we put a linker in between the carbon dot and the gold cluster. And here we have seen we put the coumarin 153 dye as a linker, And there is a cascade energy transfer, all the process we have measured, and we have seen 83% energy transfer takes place. So this is another very interesting system, and we detail, you can understand the photophysical stuff by using the ultrafast spectroscopy or any spectroscopic technique. So finally, in conclusion, the fundamental understanding for developing any kind of light harvesting system, electron dynamics, exciton dynamics, charge transfer and the energy transfer process is very important to know what is going on. So based on this, you can develop different kind of light harvesting system. These are the system JDNO and carbon dot for light harvesting. This is a very new system we have developed. Recently we are working on different kind of polymer stuff, understand the inter and intra energy transfer by anisotropy, femtosecond spectroscopy, but I don't have time to explain. And carbon dot and gold cluster for new material for light harvesting. And I must acknowledge the funding agency DASRC award and Unilever Private Limited. These are the presents. Without them I could not do anything. So thank you very much for your patience.
So good talk, Amitava. This shape effect, how does it actually come into the picture? You mentioned shape of the particle.
Shape, okay.
It was not very clear as to how the shape, if I go from a spherical to a rod to, let's say, a tetrahedron or whatever, how does it affect the dynamics of the charge transfer?
No, that is the exciton dynamics. That is not charge transfer. That is exciton dynamics. Recombination process, because you increase the trap state. When you have the surface curvature, when it is a spherical, there is a less surface curvature. The number of trap state is very less compared to the rod, compared to the tetragonal phase. That's why in case of rod shape and triangle shape, you will always get the low quantum will compared to the spherical one, because the non-radiative process is much higher than the radiative process. So this is the reason.
Is it the shape or is it the crystallographic phases which are important?
In our case, all the crystal phases are same. That is, I did not mention. Otherwise, if it is a cubic and hexagonal, then that point is there. But in our case, because that question asked actually whether that phase and number of ligands, that is important. If you change the number of ligands or different kind of ligand, that will change also the charge transfer.